In this video, I want to kind of introduce you to matrices and some types of matrices. We're going to do a little bit of we call matrix algebra, addition, subtraction, multiplication. There isn't anything like matrix division, but there's something called matrix inversion, where you find the inverse of a matrix. That's a rather complicated process. So I'm going to introduce this to some terminology um, that you need to know, So when we go to, um, some problems on matrix inversion, you will not be scared by the terminology, and so you know what we're talking about. All right, so um, let's start. So here they're telling you that, and this more suits the, the, the algebra side. There's a whole branch of mathematics called linear algebra, where you can take systems of equations and reduce them right down to matrices. And as a matter of fact, there's a systematic approach to solving these equations using matrices. And when we look at the system they're using, they could actually now write computer code to solve these equations very easily. But that's not business slant um, to matrices, right? The business applications got to do with, lots of times in business, what you have a lot of data that can very well be put to a table, right? And what do tables have? Tables will have rows and tables will have columns. And as soon as you look at these, I need to get my writing equipment together. Yes. If you look at these matrices here, you already start seeing rows and columns, right? And therefore, a lot of data that is collected in the area of business can now be reduced to simple matrices, right? As you see here. Yeah. Right. So this is what they call a row, right? So this is a row, this is a row, this is a column, right? So information that is all also in a table, right? You have the rows of a table, and you have columns, right? You have rows running across this way, columns running across this way. And therefore, anything that can be captured in a table, well, we could remove the headings and we will get a matrix, right? That's a singular of the word. Matrix. Don't confuse it with the movie, huh? Yeah. So once you have a data that can be summarized in a table, it can further be reduced to a matrix. And there are times when it lends itself to some calculation. At other times they do not, right? So that's a more business side of matrices, where you can take data that can be summarized in a table, and you can know what you call formalize the matrix, right? Form a matrix with it, and possibly do some calculations, right? And hopefully, I'm going to show you some simple examples later. So I'm going to spoil up my good. So let's talk a little about what matrices really are, right? As this to tell you here, it's just an array of numbers, right? And this is a standard way of doing it. You will enclose it with those bold brackets, right? So as you see curved brackets, they don't have to be that this square looking bracket. It can be curved as well. So I'm watching to see if I have my microphone on. Yes, it's on. Okay. I thought it wasn't on. Yeah, looks like it's on. Okay. So some properties here. You have, as I said, rows, columns, and sometimes you hear a 2 by 2 matrix, a 3 by 3 matrix, and that sort of thing. What you are referring, sometimes you hear the word order. The order of the matrix is a 2 by 2. Um, the order of the matrix is a 4 by 4. Another term they use here is what they say here. Is the dimension. The dimension of the matrix is a 2 by 2 or 3 by 3 or 2 by 3, that sort of thing. Right? So those are some terms you will hear, right? And usually when they describe it, as you see here, let me use this one. 2 by 4. What this is telling you, there are 2 rows, right? That's this one here, the top one. 2 rows there. And the last number here, 4. 4 columns. 1, 2, 3, 4. Right? So when you describe the dimension of a matrix, you spell out how many rows you have, multiply by how many columns you have. Right? So when you hear those terms, order of the matrix or the dimension of the matrix or the size of the matrix, well, you normally describe it in terms of how many rows and how many columns you have. And then when you go to higher studies in matrix, sometimes you deal with some very, very large ones. And you have to use certain, uh, ways of like indexing every single uh, element of the matrix, right? And this is an indexing system they're using, right? You notice here, 1, meaning that okay, this element here, E, is in row 1, column 1, right? This is in row 1, column 2, and so on, right? So the I is the row and the J is the column, right? So down here, what you really mean is this element is in the mth row and the nth column, right? It's kind of funny, yeah. But matrices can get very large, and especially in let's say you collect business data, you can have a really, really big chunk of data that let's say you put in a table, and you have some very, very complicated tables, right? A lot of rows and a lot of columns, and therefore, if you can find a way of representing it as a simple matrix, you never know what that can reveal about your data, right? And for those of you who are, again, you hear of business analysts, right? And those people don't really work with one set of people. They work like a consultant, And people might say, look, let's take an airline business, and they want to know they're not making money, right? And they say, look, they call you in and you have to analyze flight data. right? So you see they have a whole set of routes, and the passengers pour route and so on. You have to analyze it. And you have to tell these people which are the more profitable routes, which are the schedules that would make them the best profit, you know, which route we might have to discontinue, that sort of thing. And well, that's really higher level stuff. So you gotta learn the basics. You are learning the ABCs, right? And that's what you were introduced to here, right? So don't be anxious. Don't hurry. You got a lot of mathematics to study. You have a business to study, right? And you'll get there eventually. But let's talk about some of these types of matrices, right? And have what you call a column matrix. That kind of speaks for itself. It just has one column, right? One column. You can have a row matrix. Speak the name again speaks for itself. It just has one row. Right? Doesn't matter how many columns, but one row. Right? The name kind of tell you everything, right? I don't worry too much. But know them, right? Know when you, so you hear people talk about, I can take this data and I can make a column matrix or a row matrix. So what is the person talking about? Right? See, if you're in a certain area, right? If you're in a certain area, what happening? What happening? Yeah. What happening? And put them created an insight. Yeah, so if you're in a certain area of study, or line of work, you got to understand the terminology that the people use, or else you'll be lost, right? That's why I tell you very often, watch the show Shark Tank, and you hear the people talking about, certain things they're talking about, and so on. Uh, so when you're in a certain area, you need to like learn the jargon, right? That they use. You need to use it as well, little by little. So by the time you are, established in business or management or accounting or whatever you're doing, right? You are speaking the language of the people, right? Good. So they have what you call a rectangular matrix. I shouldn't have to explain what a rectangle is, right? So uh, they're basically telling you here that number of rows and number of columns aren't equal, right? That's compared to what we call a square matrix, right? So rectangular matrix, you have a situation where the rows and the columns are not equal, right? And that would bring us to, what the next one is. Square matrix where the number of rows and number of columns is the same, right? We'll meet a lot of these as we go. And especially when you get table data, you have a lot of rectangular matrices, right? We will deal a lot with square matrices as we go on, especially when it comes to finding inverses and so, because usually that's one of the conditions, right? Before you can find the inverse. This is a big one, the diagonal matrix. Watch this one good. Watch this one, you'll see that um, yeah, you will see that this is the diagonal, this is the diagonal. All the elements other than that are zero, right? Okay, this is the diagonal, and this is what you refer to as the leading diagonal. You hear this word. leading diagonal. Did they use that word? They're using the word main diagonal, right? Another term they use is leading diagonal. All the others, look at watch out, zero, right? So a diagonal matrix, notice the condition, has to be a square matrix in the first place, right? Where all the elements are zero except the leading diagonal. This one, very, very important. They're called the unit or identity matrix, right? And you can have a, well, it has to be a square matrix too, right? And you can have a two by two unit matrix. This one what? 4 by 4, that 3 by 3, that 5 by 5, all kinds of things, right? But notice what it is. The, first of all, it is a diagonal matrix. So it's a square matrix, it's a diagonal matrix. But the diagonal, the elements are 1. All others are 0, 0. But the leading diagonal, the elements are 1. Then there's what we call the null matrix. Null matrix, all the elements are 0, right? And the null matrix doesn't have to be a square matrix, right? Nothing says that. So you can have a null matrix that has all kinds of dimensions. The main thing is that all the elements are 0. These are not hard things, right? That's just things to remember, you know? Because people talk about matrices and they mention things, you have an idea what they're talking about, right? They have a called triangular matrix, and as you can see here, right, okay. And then it's a square matrix. Square matrix. So you're looking at a diagonal and then what's here? You see like a triangle is formed by these zeros. A triangle is formed by these zeros. Right? You can be at the bottom too, as you see here, right? So I not hear much at the right. We talk about upper triangle and lower triangle, right? So all the ones below here are 0. So all these are the real terms here, you know, your elements that you're concerned with. So upper part have numbers, the rest is 0. Right? So they call it upper triangle matrix, and then you guess the lower triangle matrix. What will happen? Up here, if you're zeros, here is where you have numbers. Right? Let me see an example here. They're not so significant. Sometimes, again, you analyze a table of data, right? Analyze a table of data, and sometimes person they're telling you about the data, and maybe they're telling you that when you look at the table, basically it forms a, let's just say use the word lower triangular matrix. And right away, that should tell you, oh, that means that oh, all these here are zeros, right? All those here are zeros. And therefore, maybe this is the problem area where nothing is happening, right? And this might be the thing for us to pay attention to. Again, like that, the flight data I was telling you about. Maybe you say, hey, let's look at why you're having these low, not necessarily zeros, but low numbers. And this is the area we should basically pay attention to. you know, see why those are low numbers or zeros, whether we should discontinue those routes or flights or whatever. This is what you call a scalar matrix, very similar to what we call a diagonal matrix, right? Um, all the numbers are equal. All the numbers are equal. In the diagonal matrix, they don't have to be equal, right? But then you talk about a scalar, usually okay, all of them are equal, as you see here, right? Here you go. You got 1, 1, 1, 6, 6, 6, 6, you know? Square matrix, it's a diagonal matrix. And um, the diagonal elements are just a single number, right? Single number. So what we want to do is we want to talk about some operations with it. Let's got a little introduction here to some types of matrix and so, right? But let's deal with some operations now. Right? Let's deal with some operations. Addition, subtraction, multiplication, and then lastly, we deal with the toughest thing, matrix inversion. Right? So okay, we're starting off with equality of matrices, right? Two matrices, if they're equal, it means that your corresponding elements are equal. And, you know, in algebra, they use this to formulate some problems. If put two matrices are equal, maybe they'll switch out some of the numbers in another one and say, well, okay, if these two are equal, what is X and Y and Z and so on? Yeah. So they're talking about some properties there. If two matrices are equal, right? If A is equals to B, then B is equals to A, right? Or all the elements of A and B, right? That's simple. What they're telling you is that, okay, if these two are equal, then simple. It means that this here is equal to 1. This here is equal to 0, the corresponding elements. This here is equal to 0, and so on, right? This here is equal to that. This is equal to that. That's all right. That is equal to that. You know, that is equal to that. This is equal to this. That is equal to that. Right? That's what they mean. Nothing complicated. Additional. Additional subtractions are right and simple. When you adding and subtracting matrices, oh, by the way, they have to have a certain condition met, right? And um, for two matrices to be added or subtracted, they have to be of the same size, same size. You cannot add two matrices that their dimensions are different, right? And all they're telling you is that what you do, you add corresponding elements, right? Add um, A subscript ij, B subscript ij, will give you C subscript ij, right? Same thing with subtraction. You subtract, right? We'll see an example just now. So first of all, the condition has to be the same. Sorry, what am I saying? The condition? The size has to be the same. Two matrices got to be at the same size. And all you do is that you add corresponding elements. Right? An example would definitely bring that out. Right? So let me go to the example. Coming to those properties here. So to add 7 and 1, you get 8. Notice that. To add these two, and you get 8. The 3 and the 5, you add them up and you get 8 again, right? You get 8 minus 1 and 6. You add them up, right? And you get 5. Simple as that. And you do that with all the other elements. Subtraction is the same thing. You just subtract the corresponding elements, right? Addition, you add the corresponding elements. Subtraction, you subtract the corresponding elements. And be careful with negative numbers also. Right? It can be very tricky. Right? It can be very tricky. And they're telling you that just like how in little arithmetic, that addition is commutative. Well, yeah. If you add matrix A and matrix B, or you switch them around and you add B and A, you will have the same thing, right? Same thing with the associative law. If you were to add this to this sum, or whether you sum these two, as you see here, and then add it to C, well, you'll still have the sum of all three, right? That's the associative law for the addition of matrices. So, commutative, some people say, commutative and associative. All right. And just like again in arithmetic, if you add 0 to a number, it remains the same. Well, that's what you're saying. If you were to add the identity matrix, that's the null matrix, right? Everything is 0 inside. The matrix will remain unchanged, right? Yeah. I think this piece is not related to this example here, not related, error here. So what this is telling, if you were to add a null matrix to another matrix, right? And the order don't matter, you will get back the original matrix, right? So just like in arithmetic, when you add 0 to a number, it remains unchanged. Same is true for matrices. If you were to add a null matrix to another matrix, it's going to remain the same, right? And you have what you call the additive inverse. If you take a matrix and you switch around the signs of every element, and you were to add it to the original matrix, you're going to get the null matrix, right? That's what it tells you. As I said, this here is not related to any of this. This is just a subtraction example. There you subtract correspondingly. 6 minus 1, you find. 4 minus 2 gives you 2. 2 minus 0 gives you 2, and so on, right? Not difficult, not difficult. Well, for practice, so you have to do them often and so, and it becomes second nature to you. So multiplication can be troublesome, but scalar multiplication is the easiest, right? Easiest. Scalar multiplication. What that really means is that you multiply the matrix by a number in front, right? It's not a matrix, just a number, right? So like, okay, if you have this matrix, and you multiply it by 4. It simply means you multiply every element here, every element by 4, every element by 4. Just multiply everything inside by 4. Scalar multiplication basically involves multiplying a matrix by a single number, not another matrix, just a number, right? So, okay, I remember this from high school, the high school matrix thing, right? You have some recipe, you have some recipe, and the recipe will have Okay, so let's say several recipes. Recipe A, recipe A, recipe B, recipe C. We'll have, okay, the ingredients here, flour, sugar, uh, okay, salt, and so on, right? Good. And this recipe is for, let's say, 1 pound of cake. We have some numbers here. And somebody said, well, all right, how much should I put if I do 2.5 pound of cake? You simply multiply everything in here by 2.5. So you take the rest, every number and multiply it by 2.5. And you now have the recipe for 2.5 pounds of cake. Right? I remember that from high school. Yeah. So that's simple scalar multiplication. And this is the example, right? So you multiply 4 by everything here, 4 by everything here, right? So you take this 4, you multiply that, everything, right? And you get 12 minus 4, 8, 4, right? You multiply this number by everything in here, right? And they're telling you whether the scalar is behind or in front, doesn't matter. That's what they're trying to tell you. And these are some properties, some additional properties, you know? So K, a scalar quantity multiplied by the sum of two matrices, is the same as if you were to multiply each matrix by the K and then add it. That's what they tell you. The order don't matter if the K is sorry, this is not that. This is if you want to have two numbers in front. Wonder, I've never seen this being applied anywhere. Anyway, if you have two scalars, you add them, then multiply that. It's the same as if you were to multiply the matrix by each of the scalar and then add them. It's a little strange property. Odd, I've never seen that before. But that's true. I can tell you that. The arithmetic, I'm playing in my head and it's same thing with the scalar multiplication is associative, right? Meaning that it doesn't matter if you have the K in front, you multiply these two and then multiply by K, or you multiply the K by A and then multiply by B. This will come a little later. You have to actually know matrix multiplication because here you have AB, which involves matrix multiplication. You're going to learn that in a few, right? Or whether you want to take A multiplied by K and then the answer multiplied by B, it's all the same. Right? Same thing here too. Whether you take two scalars and multiply it by a thing, by a matrix, it doesn't matter whether you multiply the matrix by a scalar, then by another, or whether you multiply the two scalars and then multiply the matrix, which makes no sense. Right? So all those are properties. You can't remember them. You will have them. You have an open book test. I want to go after testing. You have all of these in front of you. So now we're going to come to the hard stuff. Now you have to really pay attention. We're talking here about matrix multiplication. Here, not a scalar in front. You're talking about two matrices you have to multiply. Right? So there's a condition that needs to be met. Right? And use the word, they must be conformable, meaning they have to meet certain conditions. They have to conform to certain conditions. Right? I notice they use the word, the letter O here instead of I. I'm wondering. That's the way to spell it here. When it comes to matrices. Yeah. So what's the condition basically? right? The number of columns in the first must equal to the number of rows in the second. So a quick way to spot that is to write down the order or the dimension. And this number must equal to this number. These two must be equal. Equal. If they're not conformable, and therefore you can't multiply, right? The answer that you get in the end is the answer, all right? That's the resulting matrix. It is these two numbers, the number of rows in the first one multiplied by the number of columns in the second. Right? So it's a trick. Well, you'll see that as you multiply matrices, you're going to see that to be true. But notice the condition. Number of rows, in other words, this number is equal to this number. And the answer when you finish the multiplication will be 1 by 1. Right? Which is this number by that number. Oh, they're speaking of two specific matrices here, right? To have all the other different dimensions that you can have, right? So let's look at some examples here. So you have a okay. So if you were to have notice here, 2 by 1, 2 by 1 by 4 by 2. Right away, you know this number not equal to that number. Can't multiply. Okay. This number is not the same as that number. No, can't multiply. However, this number is the same as that number. Yes. Right? So the key to you figuring out whether the two matrices can be multiplied is that you must, the number of columns in the first must equal to the number of rows in the second. And the answer will be, notice, this two by this two. The number in the rows in the first one, the number of columns in the second. That's what you see. As you do this kind of thing, remember this is new to you. So you say, well, how are you going to remember all this and all these worries? But as you do many of them, it's going to become second nature to you. Right? It's not going to be very difficult. And you will be able to spot, especially when you do the matrix multiplication, you'll be able to, sometimes even if you don't check the condition and you start, you realize, wait, what will this one multiply by? And oh, no, something going wrong. I don't have nothing to multiply this by, and I don't have nothing to multiply that by, and you will know that you are wrong. You need to look back at the conditions. All right. So this is what they're telling you here, how to do the multiplication. I think this, you're going to see an example, right? So this might very well look confusing. Don't be scared, right? Don't be scared. So let's see. When you multiply, you actually multiply what we call rows by column, right? Rows by column. So you're multiplying this here. This is what you do. Multiplying this row by this column. And that will give you this number here. And that's what they're trying to show you, right? A11 times B11 plus A12 multiplied by B21, A13 multiplied by B31, right? So you want this multiplied by that plus this multiplied by that plus this multiplied by that. And that will give you this number here. Right? Raise and I'll go to the next one. So next, you have to multiply this row by the second column, and that will give you this one. And that's what I'm showing you here, right? Here. And then after that, move on to this. What is that? Oh, is that? Here. So next, you take the second row by the first column. That will give you this number. Right? That's what they're showing you here. And lastly, you're taking this second row by the second column. That will give you this one. Right? And that's what we're showing you here. You multiply this. Notice this number. Let me go with this last one, right? So it's this row by this column. So this number multiplied by that number plus this number multiplied by that number plus this number multiplied by this number. Add them all up and you will get this here, which goes here. And it takes some work, right? It takes some work. Look at an example here. All right, so maybe you want to check the condition. So this is a 2 by 3. This is a 2 by 3. Right? Two rows by 3 columns. And this one is a 3 by 2, right? 3 rows by 2 columns. These two numbers agree. Star, yes, they're conformable. And then you know that you're looking for an answer that is a 2 by 2, right? That's what you see here. So take this row, multiply by this column, add them all up. That's what you see here, right? And you take this fourth row again, multiply by this second column, you add them all up, and that's what you get there. When you take this second row, multiply by this fourth column, you will get this. And you take the second row again, multiply by the second column, then you get that. Rows by column. Add them all up, you'll get that. And this is a quick trick if you were to multiply what we call the unit matrix, right? By the matrix itself, the matrix will remain unchanged. You can check it out and see that it's true. Follow that procedure I showed you there. If you know this, well, you don't have to do the work. Matrix multiplication, right? This is important. You need to learn this, right? These are some conditions that we talked about to some extent. These are some operations now with multiplication, right? It includes addition and so, right? So to multiply a matrix by the unit matrix, it's the same as putting your unit matrix in front. The matrix remains unchanged. The associative law holds for matrix multiplication, right? It doesn't matter which pair you multiply first. Same thing with the distributive law. You have a matrix multiplied by the sum of two others, but it's the same as the matrix multiplied by one plus the matrix multiplied by the other, right? It's impossible, not impossible, but it will take a very, very, very long video for you to verify each of these with examples. You can on your own take a matrix, take a couple of matrices at random, one, A, B, C, right? And check that these are so, right? Check that they are so. Okay. And here they're telling you something that matrix multiplication it may not be equal to being, may not, because it might not be commutative because, as they say, they're not conformable, right? And just before, I think was Is it the previous? Yeah, no, we forgot it. These here, right? I just want to show you something. Down here is 2 by 3, and this one is 3 by 2. If I were to switch this around, you got 3 by 2, and you got, oh no, they will be 3 by 2. Yeah, oh, they are conformable. Oh, I was going to think that they weren't here. But they are conformable. My bad. Sometimes when you switch it around, you might think that you can switch it around, but not always. Keep that in mind. Not always conformable, right? And another thing is that if the two of them multiply to give you 0, it doesn't mean that one or the other is 0. This comes from, that quadratic thing. You might think that, remember they tell you AB equals 0, then either A equals 0 or B equals 0. That's not true in matrices, right? Keep that in mind. Similarly, right here, they tell you here, if AB equal to AC, don't think that, well, because A and A is the same, you can all kind of cancel A and cancel A. And that means that B equals C. That may not be so. Matrices are not like, numbers, right? They're a whole different structure by themselves, and they can be very tricky, right? Um, I think they're going to verify a couple of these things they're talking about. Oh, yeah, sorry. Look at this one. Um, so AB not generally equal to BA, right? So they give you two matrices, right? 2 by 2, 2 by 2. And they find TS and ST. And you see there are two different matrices. However, it's not that they are not conformable up here. Look here. This is not illustrating this, that they're not conformable. These are conformable. They're all 2 by 2, right? But this example illustrates that AB and BA is not necessarily the same, right? So they're not looking at conformability. I think the person who put together these slides, I don't know why they stick that in here. But the reason why here is not that they're not conformable. It's just that the arithmetic is such that AB is not equal to B. That's all. And this is another thing they told us, that if AB is 0, doesn't mean that either A or B is 0. Right? You can look at this. You have two matrices here, multiply to give you all zeros, right? Null matrix. But however, this one is not a zero matrix, nor this one, right? It's not a null matrix, nor this one is not a null. So that's possible. And again, that's matrices. They're a body or a structure all by themselves. Just before I close off this section of the video, we just want to talk about a few more things, and then I'll probably make another video, because this one might be too long for you, I think I should stop. Yeah, let me stop there, and I'll take from transpose to going down, right? I'll stop here.